That's all that I was going to do in today's video, but I do have, of course, the simulation loaded up with these masses and initial velocities so that we can play it out and see what happens. You notice that the final velocity is 0.33. The initial was 2 and was negative 0.5. And for what it's worth, we can also have the kinetic energy, which was 0.08 initially and 1.13 0.08 finally and 1.13 initially. So again, there's our before and after for this particular motion. This obviously is rounding to 2 digits after the decimal place instead of 3 as I was retaining. That's all for today's video. I hope that you've learned something from it, and thanks for watching. Hello and welcome again to my physics online video lecture series. Today's video, we're going to be talking about perfectly inelastic collisions. So let's get straight into that. I have here the PhET simulation, which I used in my previous video discussing about center of mass motion. And in this simulation, I originally showed like where's the center of mass for my system, etc. But there's a second little divider, which is this elasticity divider. So a perfectly inelastic collision is going to be a collision in which the elasticity is 0%. Okay, what does that mean? It means the two objects do not, they may change velocity individually. One of them may even reverse directions, but they do not bounce off of each other. In other words, when they collide, they stick together. Okay, so here's an example of that. The two have stuck together. They're now moving together after the collision. If I change the masses of one of them, I can do it again. Pow! And they're stuck together and moving together somewhere. And I can do that for any variety of combinations of relative masses between the two. Watch this one, pow, etc. Okay, so what does it mean that the two have stuck together? So I'm going to go ahead and close this one for now. Well, the fact that they are stuck together means that V1 final and V2 final are equal. We might just call that V final. So this is stuck together or perfectly inelastic collision. And that is the basic condition that goes with a perfectly inelastic collision. Conservation of momentum basically says m1 v1 initial plus m2 v2 initial is now m1 plus m2 times v final. Now note that this equation that I've written for the perfectly inelastic collision is actually the exact reverse of the center of mass stuff that I did in my previous video where we had things breaking apart. In that previous video, I basically just looked at the center of mass motion for our system, but conservation of linear momentum could have been invoked as well, and it looks kind of like the two sides have flipped with each other. We are, for today's video, really going to focus more on this condition, however, than this one, since I've got another one already dedicated to this. So what are some possible combinations that might occur? So scenario one. Scenario one basically has one object moving initially, V1 initial, mass m1, and object 2, here's object 1, here's object 2, object 2, V2 initial is 0. For this scenario, the equation that I've written here becomes m1 v initial, this right here could be just set to v initial since the other thing is not moving at all. m1 v initial is m1 plus m2 v final. And in fact, since there's only one vector on each side of the equation, we could even drop the vectors at this point and they will still work out all right. Okay, this is the case you'd get when, for example, you push, let's say, a billiards ball, like the cue ball, and it collides with another ball on the billiards table, albeit this collision has the two sticking together and not having one stop and the other move, or the two bounce off or something like that. So this particular collision, your two stick together. So imagine there being a billiards ball, but it has like a sticky substance on it, so that when it crashes into the other billiards ball, they are stuck together. A more common example, by the way, would be if you shoot a bullet and it embeds itself into your target, or if you throw a baseball or something like that, like throw a baseball and somebody catches the baseball or makes especially a jumping catch, then the baseball is now stuck in the player's glove, and so the two are now moving together. Okay, scenario 2 would be, what if the two stop finally? So both stop finally. For this scenario, what you have is one object moving with a velocity, we'll call this v1 and m1. And then maybe we have another object, m2, that has v2, and they crash into each other, and you end up with the two of them just kind of stopped. In this special scenario, you might say something like m1 v1 plus m2 v2 is equal to 0. And so the implication is that let's say v2, we just want maybe the speed or the magnitude. v2 will look like m1 over m2 v1. Scenario 3 is kind of all the other linear motion scenarios, and that's neither is stopped. So neither is stopped before nor after. So essentially you have a scenario like this. So m1, m2, and then after the collision, maybe we have m1 and m2. And that one is just the generalized condition that looks like this right here. And so for that one, what we would say is something like m1 v1 plus m2 v2 initial is equal to m1 plus m2 v final. And so v final simply ends up being m1 v1 initial plus m2 v2 initial divided by m1 plus m2. So what do we do with all this? Basically we can use it to solve for velocities. The other piece, and this is the piece that I'm saying that you may want to put an asterisk next to if you're not taking this in the order forces, then energy, then momentum. Like I said, there are some instructors and courses that will go forces, then momentum, then energy. So if you haven't covered energy yet, you may want to rewatch this particular lecture after you've covered energy. But if you covered energy and work before you covered momentum, then keep watching if you're at the part of the semester where you're just getting to collisions. Because there is energy considerations or mechanical energy considerations. And the mechanical energy considerations for this is mechanical energy is lost. So mechanical energy loss. That basically comes from the fact that essentially in sticking together you've done some sort of deformation, and so that in and of itself is going to pull some mechanical energy from the system. Usually you also hear a loud sound and that pulls energy from the system and so on. So these two statements basically mean that E final must be less than E initial for the system. And remember that your energy should look like 1/2 M1 V1 final squared plus 1/2 M2 V2 final squared. So this ends up looking like 1/2 M1 plus M2 V2 or V final, squared must be somehow less than 1/2 of M1 V1 initial squared plus 1/2 of M2 V2 initial squared. There may be extenuating circumstances such as one of them is on a hill or something like that, in which case you could also include an MGH on both sides. But by and large, this is what the condition implies. So that is the energy consideration. Let's end with a quick example. So we have two objects which are going to undergo a perfectly inelastic collision. The two objects have an initial speed v1 initial of 2 meters per second to the right. This object also has a relatively smaller mass of 0.50 kilograms. The other object has a larger mass of 1.0 kilograms and an initial velocity of 0.5 meters per second to the left. So after the collision, what will their velocities be? Well, we know that M1 V1 initial plus M2 V2 initial is equal to M1 plus M2 V final, all with vector signs to them. Taking the left to be negative, so negative left, positive right, then what we end up with is M1 V1 initial minus M2 V2 initial is M1 plus M2 V final. And so this means that V final will be M1 V1 initial minus M2 V2 initial divided by M1 plus M2. So if we plug numbers in that we've been given, then we have 0.5 kilograms times 2 meters per second minus 1 kilogram times 0.5 meters per second divided by 0.5 kilograms plus 1.0 kilograms. So that is 1/2 over 1.5, and so our final speed is plus 0.33 meters per second. So this would be plus 0.33 meters per second, or in other words, 0.33 meters per second to the right, since plus was to the right. I suppose the follow-up example might be how much energy is lost. So the initial energy is 1/2 M1 V1 initial squared plus 1/2 M2 V2 initial squared, and our final energy would be 1/2 m1 plus m2 v final squared. So let's fill the numbers in. This gives me an initial energy of about, let's see, this is 4 times a fourth, so that's 1 plus half times a quarter, so 1 1/8, so that's like 1.125 joules. The final energy looks like 1.5 times 0.33 squared, so this should be like n times a half, 0.083 joules. Obviously, the final energy is less than the initial energy.